Welcome to the first video on solving linear equations. Let's start by talking about what a linear equation looks like. A linear equation can be rewritten into the form ax equals b, where a is a number and b is a number, and x is our variable. So x usually we use the letter x, but we can use any letter, y, sometimes t, p, q. The idea here is that we might start out by looking at an equation that doesn't look exactly like this, but if something is linear, we should be able to rewrite it in this form where the number in front of x, that a, does not equal 0, so we don't want a 0 in front of the x. Let's look at a few examples now. For the first example, let's start with something pretty simple. X minus 2 equals 5. It's a linear equation. Some of you can probably already realize what your x should be. We're looking for a number that when we subtract 2, we should get 5. Well, that number clearly should be 7. But what about solving this in a more mathematical way? Well, the first thing we want to do is collect like terms. We want all of the terms with x's in them on the left-hand side here, and all of our numbered terms without x's on the right-hand side. So if we're working with this equation, we've got x on the left-hand side alone, and on the right-hand side we've got our 5. Now we want to move this minus 2 over to the right-hand side. And the thing to remember here to start out is that we can move things around the equal sign to the left or to the right as we want to. But whenever we move something either direction, it changes sign. So this minus 2 on the left, when we move it over to the right, is going to become a plus 2. Then from here, we can collect our like terms. We only have x on the left side. On the right side, we've got 5 plus 2, which makes 7, and there's our final answer. So the first thing that I'll point out to you is that when you're solving linear equations, you should always come up with a single answer, like this, x equals 7. This is the one number that we could plug back in to x in our original equation that would make the left side equal the right side. Let's try something different. Here we've got something slightly more complicated. What we've done here is we've thrown in some brackets. And what you need to remember about brackets is that in this context, they represent multiplication. So what this equation is saying is that that 2 in front of the brackets will go through to multiply both of the terms in the brackets. So that's what we want to start with before collecting like terms. So let's do that first. 2 times 5x makes 10x. 2 times negative 4 makes negative 8. Then on the right side, we've got 8 plus 2x. Now let's collect like terms. Let's bring all of our x terms over to the left. We've got 10x. Then this plus 2x will come over and become a minus 2x equals 8. And then this minus 8 from the right side will come over to the left side, and when it moves over that equals, it becomes a plus 8. So once we combine like terms, we have 10x minus 2x, which leaves us with 8x's, equals 8 plus 8 is 16. And now we have that ax equals b form that we were looking for. From here, what we can do is just simply divide both sides of the equation by 8, because that's the coefficient of x, and that'll leave x on its own on the left-hand side. But whatever we do to one piece of the equation, we have to do to every other piece. So if we divide the 8x by 8, then we also have to divide the 16 by 8. And what we're left with is just x on the left side. 16 divided by 8 gives us 2 on the right side, and there's our unique answer. And if we took that answer, and if we plug that back up into our original equation here, and here, we should end up with left side equals right side. Let's try something a little bit more complicated. what if we have fractions? The thing about fractions is they're messy to work with. So what I like to do is, before I do brackets, before I collect like terms, I like to clear the fractions. Clearing the fractions means multiplying every piece by a number that the denominators all go into. That will clear the fractions away. So if I look at the two denominators here, 2 and 3, I know that a number that both of those numbers go into is 6. So maybe I will multiply every piece in my equation by 6. So this piece by 6, this piece by 6, and this piece by 6. Notice that here, with the brackets, I did not multiply this piece and this piece by 6 also. Why did I not do that? Because when I multiply the outside by 6, that'll eventually come in to multiply what's inside too. So I only need to do it outside. Now, if I look at the fractions now, 6 times 1 is 6, divide by 2, leaves me with a 3 in front of that bracket. The fraction's gone. And over here, on the right side, 6 times 1 is 6, divide by 3, we get 2. X plus 12. From here, we can multiply through the brackets. So I'm looking at 3 times 1 is 3, minus 3 times x is 3x, equals, on our right side, 2x plus 12. Now collecting like terms, I'll have a minus 3x on this side. Moving that term over, that positive 2x becomes a negative 2x. On the right side, we have 12. Moving that 3 over, it'll become a negative 3, which leaves us with minus 5x equals 12 minus 3 makes 9. For the last step, we just divide through by what's in front of our x, leaving us with just x on the left side and the fraction 9 over minus 5, which can also be written as minus 9 over 5, as our final answer. Let's try another one. 1/3 times 3x plus 3 equals x plus 9. Okay, like in the last example, let's start by clearing the fraction. Here there's only one fraction, 1/3, so let's multiply by 3. Only remember, if we do that to this piece here, we have to do it to this piece and this piece also. Not inside the brackets, because this 3 will come through those brackets in the next step. So looking at what we have here, 3 divided by 3, that's gone, leaving us with just 1 in front of the brackets, equals 3x plus 3 times 9 makes 27. Now, this 1 in front of something, we don't have to write that anymore. So this is really just 3x plus 3 on the left side. So we've got 3x. Let's bring that 3x over for minus 3x equals 27. And then let's bring that 3 over. It'll become a minus 3, leaving us with, on the right side, 24. On the left side, 3x minus 3x leaves us with 0x. And here we want to beware, because remember what we said on that second slide, that to be a linear equation, you have to be able to write it in the form ax equals b, where a does not equal 0. Here we have a equals 0, which means that our original equation was not linear to begin with. What we're looking at here is 0 equals 24. A false statement. 0 does not equal 24. So what that tells us is, first, the equation wasn't linear, and second, there is no x that would have satisfied that original equation. No matter what x we plugged in, we would never get left side equals right side. For our final slide, let's do a very similar equation. So let's start by clearing the fraction. Times 3, times 3, and times 3. And we'll end up with the 3's canceling, leaving us with just the 3x plus 3 on the left side, same as before. And then 3x plus 3 on the right side. Again, if we rearrange like terms, bring that over for a minus 3x, bring that over for a minus 3. This time, we have 0x equals 0. Again, not linear because we're not allowed to have 0 in front of x, but the difference here is that we are looking at an equation that says 0 equals 0. Instead of being always false, this is always true, meaning that whatever x I could plug in at the start would be a solution to the equation. If I use x equals 1, I'll get right side equals left side. If I use x equals 7, I'll get left side equals right side. When we see something that's always true, it tells us two things. First, that the equation wasn't linear to begin with, but this time that any x would have satisfied. There's your mini tutorial on solving linear equations. See you next video.